Good afternoon, everybody. I'm happy to introduce Ramtin Haghnazar. He's a visiting scholar in the Biodesign Research Group. He's also teaching in the architecture program. And he co-founded two organizations. One is Dahi Studio, the other is Craft House. Also the winner of many awards, including an Architizer A+ award. And he's worked in Qatar, Germany, Canada, and he's here for another year and a half working with us. And we look forward to hearing what you have to say. Thank you.
Thank you. Okay, hello everybody, and thank you, Jonas, for generous introduction. I just wanted to add that I studied Bachelor of Architecture, Master of Architectural Technology, and a PhD in Computational Design. And I wanna tell the story of my journey in the firm of architecture and computational design today. I wanna start with a question that I had in mind when I studied Bachelor of Architecture. I always had in mind that why there is a big difference between other industries generation. I mean, for example, the telecommunication now from 20 years ago, or automobiles or cars now from 50 years ago. But in architecture, we are building our structures and constructions exactly in the same way that we did 100 years ago or even more. And it is the same all around the world mostly, but yeah, there is a little difference in developed countries, but not that much. I mean, in comparison to other industries, we are a lot behind. And the result is obvious. This industry, construction, is responsible for more than a third energy consumption, waste we produce, and many other disasters. And considering the increasing need for houses, buildings, and many things, we really need to reconsider how we think about architecture and how we made everything. And obviously, I'm not the first person that asked this question, and many others think about this. And one of the, actually, the answer that I really liked is this one, which shows that how digital industries are more efficient, and construction in this chart, actually, as you can see, is the worst one. When the university asked me to start to teach around 7 or 8 years ago, I started to think that how we are teaching architecture, which is about making, without practice the making. I mean, without making, we are teaching making. So I thought maybe the best way, actually the thing that I need to add to my courses is about making something in the field of architecture. And I want to add something else, that when we are talking about making and teaching in architecture, consider that thousands of years ago, when a person, anybody, want to build something as an architect that we have in mind, the builder, the drawer, the designer, all of them, most of the time, was the same person and the same group. But after Alberti, during recent, especially centuries, we had a problem that somebody designed something and someone else go and make something. I mean, when you're designing blueprints, you're not designing the building, you're just designing a notation of building. I mean, you're not talking about every single detail in the building. You just say, for example, in the big rectangular wall here. And the builder think how it starts, for example, cutting the first brick, how place the second one, how framing this, and what is the hierarchy about this one. With BIM technologies, it is changing a little, but not big difference, and still we are just thinking about the notation of the building. And consider that when you go to, for example, an architectural office, you sometimes almost never left your desk, and you're just working behind the desk and design something in the computer and don't know anything about what's happening on the real construction site. Sometimes it happens. So I started my career with working in an architectural office. After designing some projects, I understand that it is not really what I want to do. So I started a new kind of startup office things, which its actually mission was research in the firm of architecture, and especially in about making and digital fabrication. And after working on some different projects, most of our client was, and actually our builder and architects. I mean, we don't have any normal people client. And we help architects and other builders to design and create and build complex forms and new forms in general. And after that, we understand that we need a kind of a digital fabrication laboratory too, because we cannot design something 100% new without knowing how we want to make it. So we need a prototyping lab. So we founded a lab containing a robotic industrial arm, CNC milling machine, laser cutters, 3D printers that help us in prototyping our projects. And this is the image of the lab. And I want to start with some of our academic researches that we had in different universities. Actually, some of them were 2 weeks workshop. Some of them was a course, like seminar course or a studio course. And yeah, but I want to describe some of them right now. The first one was a kind of, and all of these courses, consider that all of these courses are about creating the atmosphere and space and opportunity to experience integrated design and fabrication process, but in the form of actually computational design, not normal or other method of design. So we are trying to create the opportunity for the students to experience how they can design something and build them in real scale, which at least in our university, at the University of Tehran, was not something common. So we always in our research project consider the topic. For example, here it was about kind of a reciprocal framing structure called Nextorade. And we start to think about how they works. Students and researchers first start to think how they can, actually they made some very basic models by hand, as you can see in the images. These are actually simple wooden sticks. They put them together and create some form from very simple to a little more complex. Then they extract the logic from the thing that they made. I mean, there's a logic behind these geometries. And implement this logic in a computational design platform. We usually use Grasshopper and Rhino. I think you are familiar with it, at least. And then we try to actually make some prototypes to see that our actually implemented logic or our code or design tools is working properly or not. These are, for example, some tabletop models from the logic that we had. We use laser cutter and very small pieces of wood to create something like these. And after that, we try to design our final system for our biggest structure, and we use that computational design tool to create some forms, create shop drawings, and create the final shape of the structure, final details, everything. And then we made every piece of structure by CNC milling machine or something like that, any kind of digital fabrication tool. Here it is CNC milling machine. And then assemble them together to create the final structure. Consider that when we are using a computational design tool and digital fabrication tool, actually we are using computer or robots, kind of robots, very simple robots, I mean, to fabricate the elements. So they don't have any knowledge or intelligence, a special kind. You have to model every single aspect of your pieces or your design, every single bolt or screw, everything that you have in the in your construction. I can compare it to when you build something or model something in your computer and 3D printed it. When you are 3D printing something, you have everything on your computer. I mean, you are not designing the notation of the building. You are really designing the building because you are designing every single piece, every single part of it. And finally, we build something like this in this research. For another research, another example, we started to think how we can create kind of all of these structures that I'm showing today are non-standard buildings, non-standard construction. I mean, we don't use standard pieces, I mean, similar pieces to make something like this. For example, this one has around 400 pieces, and all of them are different together with each other. And so we make all of them one by something like CNC milling machine or any kind of digital fabrication tool. For this one, we start to think how we can make something like this by bamboo, which is a more sustainable material, actually non-industrial material. I mean, before even starting fabrication, they are different from each other, so we have to have some knowledge about the material. So we started studying it. What is actually the thickness of it, what is the normal diameter, what is the strength, and then study the previous works, the literature of the area, and finally design some systems, I mean some prototypes that we can actually makes us able to create something freeform. And these are some samples that we made in our lab. And after prototyping, we make a decision which one is better for us. And sometimes even standard digital fabrication tools are not suitable for you, so you need to hack them or modify them in a way that you can use to create your specific pieces. For example, we couldn't find this long, actually, rotary CNC milling machine, so we hack our normal CNC milling machine and add something to it to make us able to build these kind of elements. And finally, we assemble them together. It takes 1 day approximately to assemble this. It was about 1,000 square feet structure. I mean, the area is 1,000 square feet. Or another one was a kind of a commercial academic project. I mean, it has a special client that ordered this. It is about making a freeform surface out of GFRP, grass fiber reinforced polymer. I think you are familiar with the material. There are many small objects made by this material, usually used in industrial design, for example, scales. I mean, object scales, not building scales like this, because you always need a mold bigger than your object. And for a structure like this, which has a span of more than 20 feet, it is really big mold if you want to build it. So, and it is really expensive. So it is not the way that you can do it. We start to think how we can actually delete the mold from our process. So we form something with fabric, which is very, I mean, cheap and simple, and then start to actually kind of deposition the material, something that can fix it and make it stable in its position. And make our surface. These are the first prototype that we made. And as you can see on this image, in comparison to its thickness and its size, it is really strong that can actually carry the load of those amount of bricks and nothing happened to it. And then we start the process with prototyping different objects in different form. We use different materials, mostly resin, to actually make them fixed. And after that, we design our final prototypes based on our experience and what we understand from the prototyping. And finally, start to make the big structure. And it was an interesting thing. We create a big scaffold and use form-finding methods to create the fabrics, actually in the specific position. And then actually try to shot material, actually layer by layer resin and fiberglass to it to create this form. For example, this form with more than 3 meter cantilever each side, I mean, it is more than 10 feet, for example, just has a thickness of less than 5 millimeter in the end. And it is because, because when you are making something with these form, actually using form-finding methods and create kind of a double curved surface like this, it is really high performance, and as you can see, it is very stiff. And even when we wanted to detach the scaffold. We thought maybe it may shake a lot or transform a little. But after detaching the scaffold starts to shake and it's stand in its position because of its shape. It was very stiff. Or another research was about making something with use of actually robotic arm, industrial robotic arm. We think how we can use a robotic arm like this to build something with it, just build something. And one of the easiest way that you can use these robots are using the pick and place strategies like this that robot can pick something or brick or a kind of module and put it in a specific way or a specific position. And then by stacking them together, you can create lots of different forms in different situations. So we studied about it and tried to find different methods to make it stable and beautiful or something. And finally, we designed a kind of a vault in an architectural scale. And obviously, even big robots are really tiny in comparison to the scale of the building. So you need to actually split your surface to, for example, here we divided it to 9 different pieces and build the pieces one by one. And when you were doing this, you need lots of simulation, analysis, and many things. Because, for example, when the robot placing the bricks one by one, so in your model, you need all of the bricks one by one because you need to know all of them, the position of all of them, and many information about them. And sometimes like this, your final installation is stable, but a piece of it is not. So when, for example, here, the robot start to place our blocks, the red one will fall because they're not, actually the pivot of it or center of it is not have overlap on the previous block, so they will fall. So during the installation, actually the fabrication process, we place some extra blocks just to keep it in its position and finally make our pieces and merge them together to create our installation like this. And these are made from a kind of actually plywood, around 4 centimeter, 1.5 inch wide for each plywood. So as a shell, it is very thin still, and it is hollow too. Okay. And the next research was about how to make kind of a surface, freeform surface, by suspending elements from a bigger frame like this. We start to think how we can actually finalize the position of our plate in an exact and a specific position on the space with just using the cables. The dimension of each cable is important, so we generate the model. We extract all of the fabrication data. For example, here the most important one was the length of each cable because they actually finalize the position of each plate. And then we cut the cables in a specific dimension and assemble them together to create this small installation like this. It was very cheap and very easy to assemble in comparison to the others. Another one was, actually it was about performance of the material too. We thought about how we can use thin shells, actually plywood shells, something like this, to create something. And we start with bending elements, so it is a kind of a surface active or bending active structure. We start to prototyping actually some small and tabletop pieces to just generate the system to understand how we can work with them. All of the prototyping phase, the first one, is made by hand, obviously. Then we extract the logic and create our design tools and use the code to generate the bigger structure. So we made some samples like these, for example, and finally we've selected one of them and then design a form considering that logic that we created and we developed. And these, for example, arcs, actually this arc contains several small pieces because each strip that you can see in this image has around, for example, more than 10 feet long, so you cannot make one of them at once. So we made them from several small pieces, then tailored them together, joined them together. And each arc, actually, which has a kind of a V section as a folded plate, has two pieces like this. And when you join, and we have the specific points on each side that you can join them together, like, for example, close that you have some button on it. And when we join them together, it gets its own final shape because of the feature of the material. So it becomes this way. It is the, for example, first arc that we assemble. And after that, we join all of them together. Once more, I want to talk about the material performance. This vault with, it has a small span, but more than 10 feet still. It's made by 6 millimeter thick plywood, around 1/4 inch. It is folded and bent. During the fabrication process, one of us goes on the top of the structure to just tighten the final bolts, and it didn't change, its shape didn't change a lot. It was super strong, even more stiff than what I had in mind about the structure, and it was interesting. Most of the time, we are not able easily, I mean, it is not easy to simulate these kind of a structure using computational tools like FEM analysis software that structural engineers use. So we usually just guess about it and do this by prototyping. So we made some small prototypes, test them, and see how it works, and get some kind of intuition that we can build something bigger or not. And sometimes they fail, and it is part of it, because you are making something new, something 100% new, so you don't know anything about the structural performance. For example, the Bamboo one was approximately after 1 month or 2 months after the first biggest storm collapsed because of the joint that we didn't consider that, for example, wind load, rain load, because it's become wet and become heavier, and so sometimes this happens. But not all of this. There was lots of other researches that we use different methods. For example, this one made from 3D printed joints. All of them are just about different ways to create non-standard buildings and how we can actually see the material in a different way. And obviously, we don't just research because of the research. We want to use this research in the professional projects. So I want to continue with some professional projects that we use the same exact logic to create something in the real world as our job, actually. And this is the first project that I want to talk about, and it is one of the first professional projects that I did. It is a kind of a second skin facade on top of a current actually building. For these projects that I'm trying to present right now, from this point I mean, these are the Dahi studio project, and as I said, our clients were architects. So we are not architects in charge of this project. We just help them to develop their ideas, make their prototypes, and generate the design tool, I mean, inside the computational platform, then build the one that they want to build, actually. For example, for this one, the main client wanted something from brick because it is a kind of a traditional material in Iran. As you can see, the other buildings in this image are made by brick too, but in a kind of a modern way, not in a traditional way. So we start to think how we can use brick in a different way in a structure like this, and consider that the privacy in some region of Iran especially is a very important thing, that, and after people buy apartments like this, they usually cover the balcony, so we think that maybe we can do it ourselves in a way that we like. So the whole second skin had a kind of idea like this. We start to think how we can make something with brick. The first thing that we had in mind is just by rotating this, the final installation is actually stable and static. but they placed in this position, in a rotated position. And just by rotating this, we can control the privacy, the light, daylight, and the view, and many things. So we decided to use this logic to create something on this facade. And we consider different aspects of it to make something in the end. So we made some prototypes, and finally we reached out by code that can help us to create the geometry. Because when you want to model something like this, for example, this building, this facade, have 8,000 bricks, and you need to model them one by one. You need the model of each brick in your fabrication process. And you cannot use, for example, normal 3D modeling software to create something like this. It is not, I mean, you can, but it is not efficient at all, and you cannot develop your design in this way. So we usually develop a kind of a special computational design tools for each project that can make us the main designer to easily play with it. For example, just have 20 control points that playing with this can create different alternative. So you can easily generate alternative, and after generating each alternative, you can easily generate your fabrication data that I want to talk about it. For example, here we have a small cluster containing 4 or 5 block of bricks. And they have 2 holes in it that specify actually and define their position in this column. And we use CNC milling machine to actually make holes in 8,000 bricks differently. And after that, we place them in a specific position to make the final structure like this. Another project that I want to talk about actually has the same concept, but in a different way. It is the second skin for a residential building in Toronto. But it's made from wood because the client wants something like this. We start to design something actually as a kind of a curtain in front of the building. But in this specific project, the client wanted it as a kind of a transformable. I mean, they didn't want to cover their windows always, so there are a kind of a platform on it, transformable platform on it, that can retract the elements and make a view for the people inside. So you can control the shade and anything in the structure. These actually, to build these elements, we need to put a small and kind of a thin layer of wood on top of each other and glue them together to create that form, because it is a complex form. And all of them are different from each other, like other projects. So we start the prototyping in our lab. We create different actually pieces for our layers. Each element has a kind of approximately 12 feet length, each element. And we place them on top of each other and use a mold to form them in its final shape, like this. And after a day, we could have our final element, which was something like this. And for prototyping, we used 2 different materials, for example, for this project. One of them was a kind of a timber, and another was 6 millimeter thick plywood, which, because of some reasons, we continue with plywood. It was easier to use, so we decided to use that one. And so for each single part, we had to make the mold because it is different from the others. And then every day we made 2 molds, for example, and pressed the elements on top of each other and glued them together to create our pieces. And finally, because we made this project in Tehran and ship it to Toronto, actually from Middle East to Canada, we had to make our own container, because normal standard containers couldn't, actually our pieces didn't fit inside it, because that actually cassette shape thing was the transformable part, which shipped in an assembled position. So we need to build our own container and ship it to the Toronto, and there they install it, and, excuse me, okay. And finally, this is the final images of a structure. For another project, it's very similar to the other one that I introduced as a kind of a floated plate. This was a kind of a big office with very actually tall ceiling. They wanted kind of a false ceiling, but kind of a freeform one to actually define a specific height in different space of this office. So we use that concept and place many circular plates in the space and try to use cables to attach them to the ceiling and place them in a specific way. When we start to design this project, first I thought by 3 cables we can specify the position of the circles, so that's not big deal. But after making our prototypes, we understand that, yeah, you can specify the position, but you cannot define the tilt because it is important that which angle do you want to install it, fix it. So you have 6 degrees of freedom and you need 6 cables for each place. And finally, we had thousands of cables to install all of these elements. And in this project, we couldn't attach cables to every single point that we need on the ceiling. So we had specific points. We actually surveyed them and import them to our computational tools and finally generate the length of each cable. We use kind of a circle packing algorithm to create our surface out of these circles. And this is the fabrication process. In these kind of projects, it is actually the lengths of elements, lengths of the cables are very important because if you change one of them, the tilt or position of the plate will change. We didn't actually, I don't know any other tools, digital fabrication tools that we can use to cut, for example, cable in a specific length and create the hook, because when you actually add the hook, the length will change. So we actually kind of create our own ruler. It is a big one that you can see in this image. It is a 4-meter long, 12-feet ruler and have 2 actually nuts and 2 bolts for the hooks. So we could fix it in a specific dimension. Then we use the 2 bolts to actually create the hook on the 2 ends of the cables. And so in this way, we could create each cable in a specific distance. And then we tag them, each of them, because we should know that where it should place in our structure. And all of them were different from each other. And this is the way that we create this surface. For another project, we invited to create something as an installation for an entrance of a festival in actually kind of a biennale in Iran, in Tehran. And we started to think about a gate and the technique that we developed in our previous researches before. So we think about a kind of a vault or kind of a gate for these things, and we develop our surface. We had the structural system, the next storage that I showed previously, but we a little actually upgraded because it is a commercial project, so the quality matter. And then we use a CNC milling machine to actually fabricate hundreds of elements like this, and then we paint them. And we assemble them together. Actually, for this structure, it takes 1 day only to assemble something like this. And this is the final structure that we made out of these pieces. These are actually, we made our elements out of 18mm thick plywood. Yeah, and these are this size, 2 feet something in average. Or another project that we had was kind of another false ceiling for an office. And the designer actually was someone else. We just helped them to generate that computational design tools that help you model something like this easily by some clicks only and remodel it easily one by one to generate different alternatives and finally select the final one. And it contains several suspended elements with different lengths in a specific position. By logic, it is similar to the previous projects that I mentioned in this presentation. Or another project that I involved in it was building a kind of a tensegrity structure. Tensegrity structures are famous because of their performance, so we wanted to understand how we can make something like this as a tensegrity structure. This is a tower about 30 feet long. There are several structures like this. We just wanted to analyze how we can use this. So we start with prototyping like other structures. At that time, unfortunately, Grasshopper was very new and there was not many computational design tools available for simulation specifically. So we made most of the our prototype by hand. Then we use a software like 3D Max or AutoCAD to create our final model and make something like this arc or that tower. And about the performance, I should say, for example, that 30 feet height tower had weight about less than 500 pounds. It was really light in comparison to something similar, but it was not that stiff. I mean, it moved by wind easily, something like that. It is not just about a small project. We had several, actually we can use this logic, I mean, in big project too. For example, this is another project in Istanbul we participated in. The point about this project, the rest I want to show that are some of the professional opportunities in this field. Most of the time, as I mentioned before, the architects in the architectural office, sometimes at least, do not pay attention about details, just create something. For example, for this project, they just prepare a kind of a wire mesh as the first diagram that you can see there about, for example, creating this surface, not anything more. And when you want to build something like this, you need thousands of panels. I think for this one has a 4,000 panel. And because it is rotating and twisting and it changed the shape from a square to kind of a star shape, all of these panels are different from each other. I mean, for each panel we have 4 repeat, but just it. I mean, still more than 1,000 different panels is available actually in this structure. And we need to actually create shop drawing for every single panel in projects like this. And every panel made from different elements as a frame, different gaskets, different layer of glass sometimes. Actually for this one, 3 layers of glasses. And many other things, many bolts and holes, the cut that you need for every single elements that you have in your panel. So there are lots of decisions that you need to make to create something like this, making these panels, and then assemble them together to create the final structure. And for this one, for example, we actually develop a kind of a generative tool that get the wire mesh and generate the shop drawing by itself automatically. That we had these things in our previous projects too, but this one is a little different. And so we generate that tool and we create all of the shop drawings, but that tool, or we call it kind of BIM model, but with high LOD. Or similar thing about this project, this is a company, our client was a company that built this kind of a structure. So this structure is not our design. We developed the design tool for this kind of a structure. For this structure, actually it is a little worse because most of the time architects just provide kind of a surface, nothing more, not the wire mesh, just a surface, a kind of a Nerbin Rhino or something like this, and the rest is the work of the fabricator or contractors. So one of those fabricators contact us to create something that convert the only single surface to a kind of a beam model containing every single element. I mean, every bolt, every joint, every pieces that we have in this structure. And to create something like this, you need to solve some geometrical problem. I mean, it is not something very complex. It is just about mathematics and geometry. So to reach the final shape of each joint, you need to solve, for example, several mathematical problems. And if you know it, you extract this logic, you can implement it on a plugin for Grasshopper, for example, this time we used. After that, we actually gave this plugin to the fabricator, so they import the surface and get the final shop drawing for every single piece that they have in their structure. And they made several structures with this plugin. It prepares joints, the final geometry of joints, G codes for actually milling machine that needs to create the joints, the pieces you have as elements and layers of glasses. And there are several projects like this. For example, this moat tower, it has the same story. The thing that we had was only a surface and kind of quadrangles, which were not a planar quadrangles because because of the twist of the form, if you want planar pieces, you need to cover it with triangles, not quadrangles. So these panels are a little twisted. We unroll them, use the structural system that they use actually to kind of translate it to a model that we can build in a planar position, and when you tilt it and twist it, you reach the final form. So we actually use the kind of inverse technology to understand what is the fabrication data for this project. And we actually had a chance, I had a chance in this time, and to actually work on a course with Jonas in Virginia Tech, similar thing, about entitled Integrated Computational Design and Fabrication. It is exactly the same thing that I described for you. So in this project, we had a question that how we can use bamboo to create the structure, but in a different way that I cannot describe the details here right now. And we try to, students try to generate different forms, create some tabletop models. We had a very great review session. And finally, students had a poll and select one of the form, which is this one. And it is a kind of a big form. I mean, for example, height is more than 12 feet, and the span is a little bigger than 12 feet, for example, for each part. And finally, we actually decide to create our own structural system, and we made some prototype to see how it works, and it works structurally or not. And then we actually assemble it to just test it, how it works. And right now, these days, I mean, we are making the elements. It contains more than 300 elements. We are using RDF facility to generate, actually, and create all of the elements one by one. And we hope that we can assemble the final structure in the end of the month. We need to see that it works or not. And finally, I want to say thank you to having me. And if you want to read more about this project, you can use this QR code to see my other projects too. Thank you so much.
Are there any questions from the audience?
Say, what adhesive holds this one together?
Which project?
Is it glued together?
Which one?
The one on
And this one? Yeah, it is partially glued and nailed. Yeah. This is the actually robotic placement. We had a kind of, I think it was successful prototype that when a robot picked the elements, actually we had a glue feeder and it's roll it on the glue feeder and place it on the final position. Yeah, but my teammates finally decide to change it and add nailing to this. Yeah, but I think the glue was working. Yeah.
I'll ask you a question then. So tell us about some of the differences in your experiences working with students in Iran and here, how things are different, and any insights you might be gaining from being here.
Yeah, actually, I don't have lots of experience here. It is at the first semester that I'm teaching in Virginia Tech, and it is not finished yet. But I had teach actually for more than 7 years in Iran for this similar topic. The main difference that I can say is that because students who studied architecture in Iran have a kind of a stronger background of mathematics, they can deal with these problems more easily sometimes. This is the only main difference that I can see, but it is not true always because everywhere you can see the students. The main important thing is when somebody wants to participate in this actually area, it is all about, not all about, but the most specific, actually the hardest part is about geometry, 3D geometry, solving 3D geometry, and the algorithm that you need to extract from the logic and implement it in the code to actually make a kind of a generative design tools that can regenerate everything for you. And so if everybody knows about these two things and can deal with these two problems, can work in this area easily.
And how about any reflections on changing material palette here, growing into the challenges with working with other materials?
Yeah, for every single professional project that I had, and for most of my research, we always use industrialized material, which, for example, for that brick facade, we had 8,000 bricks. All of them are similar to each other. But in our new project that I described here in the end, we are using with kind of a natural material, for example, bamboo, that they are completely different in shape, and you cannot cut them at every part that you want. So you need to have a different system to work that lets you cut it whenever you like. And you need another kind of different method for fabrication because you don't know the start point. So you need kind of tools that can ignore them or understand them better. So that's it.
All right, last chance for any questions.
Hello. You started off with asking questions about how architecture can contribute, particularly you were showing, I think you're talking about housing conditions, trying to produce more housing. So I was wondering if you had thoughts about how this work, which is really interesting in dealing with really complex forms and geometries, starts to translate or works in a different way to going back to those building conditions.
Actually, that question had two different parts. I mean, first, it was about shape, that it is always the same. And second, about the technology, which is not sustainable. About the shape, so it is obvious that computational design can reach different way and methods to generate novel shape. It is easy to create these kind of things with computational design tools. But about the sustainability and actually increasing performance, we start to work, actually we had the opportunity to work on high performance structures. And we actually deal with it in this way. And we had some other researchers, kind of an ongoing researcher, that we are trying to actually increase the performance of fabrication, but in normal condition, I mean. But I couldn't have a chance to present them here, and still we didn't have any result yet, so that's it. You mean by cost of the project? In the professional project, obviously it is expensive thing, but not always. I mean, in most of these projects, for example, consider that in most of them, we install them in a day or two, something like this, because every elements are ready to use and you can install them very fast. And so, I mean, it increased the time you need beside the actually behind the computer, but decrease the fabrication process actually sometimes, specifically assembly process, and it decreased the amount of material that you use. But still, because this technology is not that global, so for example, using CNC milling machine is expensive right now. But for 3D printing, I think it is solved right now because there are lots of 3D printers all around the world. So it is not an expensive technology these days. But yeah, I mean, from some aspects, they are even cheaper. But for this project up to now, yeah, they are sometimes twice or triple cost of the normal thing in the structure. And we had mistakes too, because there, for example, some of them was the first experience, and after that we find out that if we use a different way to do it, we can use cheaper material or cheaper technology.
I'll make another comment towards that. I think some of this is also a question of what the priorities of the project start out as. So for instance, if you said you want the project to have very little labor, then the way you design the solution, the way you parameterize it would take into account labor. It's not as if it has to be expensive. It's just when when the project is to be unique, the priorities are not cost in this case.
Yeah, and I can add something else. Because we are modeling every single part, so we have very big data about every single piece in our structure. And actually, literally, some of these projects are really wasteless. I mean, we use every single part of material. Even, for example, for the project that we are doing right now, when we use some part of, actually we have an inventory, I mean, a file in our computer that how many bamboos we have and what is the length of each node or for them. And when we use part of it, we update the library in time, and so we know what's the rest, and we can use it in different projects or different places. So for about actually material usage, I can literally say it decreased it a lot dramatically. But the technology is a little more expensive these days. I cannot hear you. Yeah. It has a very simple mechanism that you use for example, normal curtain in your house. It's just a wire that retracts the final elements. So actually they stack together, and so you have them inside. So it is just a rail, simple rail. That was not very expensive for you.